So this is fun. We are now going to take our regions and we are going to like elevate them in a certain geometric shape to create a three-dimensional object. Okay, so like this right here, I have a region, and if I slice it like a loaf of bread, the cross sections would be semicircles. Okay, doesn't matter. Okay, here you can see these look like rectangles if we were to slice them and open it up. Okay, so when I say volumes of known cross sections, that means we're basically taking something in our plane and we're raising it up to where when we slice it, we see the same geometric shape that fits in that region. Okay, and I'll show you some pictures here pretty soon. So what we're gonna do, let's talk about integrals and how integrals like add up things, right? If I were to ask you to find the volume of each of these slices, they're all basically a prism. Okay, how do we find the volume of a prism? Any prism.
Like area times base.
The area of the base times the height. Okay, well, if we're cutting these into, okay, if we're cutting these into slices that are super duper thin, then the height is going to be considered that dx or the dy. Okay, so when we find the volume of a known cross section, if it's perpendicular to the x-axis, we are going to take the integral from a to b of area times thickness. If we're perpendicular to the y-axis, we'll go in terms of y. Okay, so this is what we're working with. Show you some really cool interactive things here pretty soon, so you can get a visual of what the heck is happening. Okay, Quinn? Okay.
Yeah, it was.
But it's coming.
Oh. We'll see. I'll be able to.
You need to be able to know how to find the area of objects. Can you find the area of a triangle? Can you find the area of a semicircle? Can you find the area of a rectangle? If you can do that, you're going to be just fine. You're okay. You're okay. All right. Oh, wait. What is your I figured it was first, but I didn't. I love that we're wearing it. TBH.
When it was a pet. Oh, I know.
Because I love. That's why. All right. So let me take you to GeoGebra. I was looking at teacher's big pictures, so mind me.
this is shared. worksheets, this is what it
Yeah.
is.
Oh, come on. Internet's a little slow. Okay, here we go. Okay, so notice how I have a region between like two sine curves is kind of what it looks like, okay? And here's what it would look like. I'm trying to, okay. This is what it would look like from above, like top minus bottom, like here's my region, okay? And from our region, we are going to raise up. Why can't I get it back? There we go. Do you see how I like raise up these triangles? Okay. And as I like go through, the triangles change shape based on how far apart those two curves are. So the further apart the two curves are, the bigger that triangle is going to be. You see what I mean? Okay. Or I could say they're squares. Okay. So here's a square. Square, 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 square. Isn't that so cool? Or we can make semicircles. Okay. Okay. Or we can make isosceles right triangles. Okay, this is what we're doing. So what we're going to do is we're going to figure out the area of each given triangle based on the region and then throw it in an integral. Okay. So here's our first example. We have the volume of the solid whose base is bounded by the graphs. Y equals x plus 1 and y equals x squared minus 1. And we have cross sections perpendicular to the x-axis that are squares. Write down what you want to write down, and then we will draw the picture and go through it together. Okay, x plus 1. I'll do that in red. Okay, and then x squared minus 1. There we go. We get these shapes often, don't we? Because it'll like parabola and line intersecting to like a teardrop sort of thing. And since we have cross sections perpendicular to the x-axis, I'm going to draw in a rectangle. It's not a rectangle. I'm going to draw in a rectangle with thickness dx. Okay. Now, notice I drew that rectangle, and that is the base of whatever shape is popping up out of there. So like this is the bottom of our shape. And then in this case, we have squares popping out. Okay, where this is the base of our square. So I am going to draw this right here. It doesn't matter what the shape is. This is our base. Okay, let's talk about the length of our base. What is the length of this slice right here? Well, since we're going in terms of dx, we need to take top minus bottom. Our top function is x plus 1 minus our bottom function is x squared minus 1. Okay, that's the length of our base. Now, that's going to be the same no matter what we do. What changes now is what the shape is. Well, we have squares. Oh, let's do P. Okay. So we have a square. And I know that the area of the square is side times side, right? Or in this case, base squared. Okay. So when we go to write our volume, we have the integral of our area times dx, which is the height. Okay, now if you want to make that look prettier for the base, that's fine. Like if you actually want to distribute the negative and combine like terms, but I don't really care. Okay, what's the last thing that we need? The limits of integration is, I think, what you were trying to tell me. Yeah. Okay, well, we know this one right here for sure on the left, that is -1. What is this top one up here? You know that for sure? Let's try it. 2 plus 1 is 3 and 2 squared minus 1 is 3. Okay. I just gotta make sure. All right. So first of all, do you have a question about this setup? Area of the square dx. What? Yeah. Uh-huh. Or if we're dy, it's going to be right minus up. Yep. All right, get those calculators out and math 9 this bad boy for me. I do love math 9. Yeah. Yep. It does not need a pi out front. What did you get? 1.5. Do you agree with Aaron's 3/2? I don't think Corinne does.
No, I definitely typed it in wrong.
Okay. Corinne, what did you get? Nine halves?
9/2. But I actually
81 tenths? You want me to look at it?
You didn't square. the whole
didn't
thing.
square the whole thing.
No, you did not.
Also, that's 1/10.
Makes a big difference, huh?
I know.
81 tenths. And you knew how to write that as a fraction without your calculator telling you, right? 8.1, 81 tenths.
Yeah.
Yeah. I won't judge. I'm not going to be upset about it. Okay. All right. So Aaron, we got it.
Yes.
We fixed our calculator, user error. Okay, so now let's take the region bounded by y equals x and y equals x squared. And let's make slices that are perpendicular to the y-axis that are rectangles whose height is twice the base. Take a moment to write down the information so that when we go through this and you look back later, you know what's going on. The color of the font, I'm sure is very bright. It's like hard to
See, that sounds very standard.
They probably don't serve me in the class.
Makes sense.
They're funny too, they're the same.
Yeah. I've never been. How many years have you been? Okay, are we ready? First, we got to do our drawing. Okay, so we have a line intersecting a parabola, right? Once again, we have that weird shape. Okay, so we now are going to have cross sections perpendicular to the y-axis. So we need a rectangle with thickness dy drawn in our region. Okay, Quinn. You're like throwing your pens around.
Or because if I use the block, I'll erase this.
Okay, so our base. How would we describe its length? This rectangle right here, this slice, how long is it? So, well, but we're dy, right? So it's our blue square root of y minus our red y squared. Do you agree with that? Okay. Now, we are going to do that for every problem. Caitlin, do you have a question? I don't know. I was thinking that this was square root of x, but it's not. Thanks. Okay. All right. Square root of y minus y. Although when I said, do you agree with this? It did take one voice, but we can be quicker. Okay. So every problem that we do, we figure out the base the same way, right minus left or top minus bottom. Then we can draw in our shape. Well, we have rectangles whose height is twice the base. Well, if the base is radical y minus y, then their heights are 2 times the quantity radical y minus y. Okay, and how do we find the area of a rectangle? Well, we take length times width. All right, so the volume of this is going to be the integral from 0 to 1 of length times width dy. What is it? You said something about a 3. area dy. Now, are you okay with how I wrote the area? Length times width. I just got kind of lazy and I just put a square on here.
How come that way if you-
So, or you could write 2 times radical y minus y times radical y minus y dy. So like there's length, width. You see what I'm saying? You know what? It's not gonna matter. Either way is fine. Okay, Isaac's finding us the value. Oh, you weren't?
I mean, I am, like, I didn't really know.
Oh, so Kylie got a decimal. At the same time, ready, set.
0.066.
Okay, so it's 0. So it's repeating.
Yeah.
So this can be a fraction. Our cap,
No, it can't, because there's 7, 8 on the end.
okay,
Gosh, no,
you got it.
61 or 67. Right.
All right, we're going to do one more. In the next 5 minutes. We are going to take the graph y equals square root of x and the graph y equals e to the negative x, and we are going to have semicircles. Why am I allowed? Why did I write calculator permitted? Because our graph of e to the negative x, like this, right? Nope. E to the negative x. Perpendicular to the x-axis. So like what? Okay, I need you to be able to use your calculator to find that intersection point because it's not going to be something we can solve for without a calculator. So that is what we're gonna need out of this right here, okay? Is Connor's working on it, so is Quinn, so is Kylie and Aaron, and Matthew, and Carolyn. Matthew already found it? The intersection point? Okay, okay. Did Connor find it? Maybe. What did you get? Okay. All right. So since we only have 2 minutes, I'm just going to push through this. Okay. Now, our base. Well, look at that rectangle, top minus bottom. We have e to the negative x minus square root of x. Do you agree? Okay. Now, our shape is a semicircle. How do we find the area of a semicircle? 1/2 pi r squared. Okay, so we have the integral from 0 to 0.426 of 1/2 pi r squared and then dx. Is our radius e to the negative x minus radical x? No, this is our diameter. So we have to cut it in half for it to be our radius. So we can just cut it in half for our radius.